Hello friends. So today we are going to solve 5 questions, and these 5 questions are basically with respect to the capacitors, or we can say in general the electric field around the conductors. So this is the, and one second. So we are going to solve here 5 questions, and so let us start with the first one. And these questions are somewhat, you can say, the statements looks like they are almost same, but slight, you can say, difference is there. So we are having this first question, and in the first question it states that if the capacitance in the figure A is C, what is the capacitance in the figure B, where a third plate is inserted and the outer plates are connected by the wire. So basic figure A and B are given to us, and in figure A we are having a parallel plate capacitor, okay. And then in figure B we are given that a third plate is inserted at the midpoint, okay. So this is the third plate and the external plates are connected through the wire. So this is the basic difference between the two, and we are supposed to find out what the capacitor is going to change, especially, or we are going to find out capacitance in figure B, okay. So we are going to start with the basic formula for capacitance of a parallel plate capacitor, okay. So you can see that we are having two parallel plates, and with this separation is our, in this case it is given as S and area is given as A. Therefore we can write, especially for this with respect to figure A, or figure A, we can say that the capacitance in general, the formula will be applicable here, epsilon naught A upon S. So this is our parallel plate capacitor. And now we come to our this figure B, and figure B we can clearly see that for the time being let's ignore this wire part, okay, and we are having now two capacitors. The top one we are going to call this a capacitance having C1, and the bottom one we are going to call have a capacitance C2. Okay, then we come to the wire part. Therefore we can say that in figure B, okay, we have considered our capacitance C1, and this capacitance C1 is between our top plate and the middle plate. And area is same A, and the distance is our S by 2. Separation between the plate is S by 2. Therefore we can write that our C1 will be equal to epsilon A S upon 2, or we can say this is equal to our 2 times C, okay, because we can easily replace this part by C here. Now we come to our C2, and C2 is between the middle plate and the bottom plate. middle plate and the bottom plate. Once again, area is our A and the separation between the plates is our S by 2. Therefore, we can write that our C2 will be also equal to 2 times C. Okay. So both C1 and C2 are nothing but our 2 times C. Now we come to that the connection. So we have our that the external plates, or we can say the topmost plate and the bottommost plates are connected with the wire. So which basically means that these two plates will be at the same potential. Okay. So let me draw the figure. So this is our topmost plate and this is the bottommost plate, and there is a one in between them, and these two are connected with the help of a wire. So let us call this a plate number 1, this is plate number 2 and plate number 3. Okay, so plate number 1 and 3 are connected, so they are at the same potential. You can say plate 1 and 3, they are at same potential. And in terms of our electric circuit, let us define this in terms of our nodes. Okay, so we can name, because 1 and 3 are short circuited, okay, so let's call this as a node A. So we are going to call this as node A, and this we are going to call as node B. Okay, this is A and this will be obviously at the same A. Therefore, we can say that call this node as A. Call this node as A, and the middle plate we are going to call this as node B. Middle plate we are going to call this as our node B. So it means now our C1, which we just found our capacitance, is between our A and B. Okay, is between A and B, and our C2 is between B and A. Okay, the sequence matters, okay, because then we are able to find out whether they will be in series or they will be parallel. So that's why their sequence is important. Okay. And therefore, from here we can draw an important conclusion that both capacitors are between the same two nodes. Okay. So we can say our C1 and C2, they are between same two nodes. Same two nodes. Okay, and if you look carefully, that let me draw a figure. So this is one parallel plate capacitor and this is the other parallel plate capacitor, and if they are connected with each other, something like this, and so we can clearly see that both these capacitors, okay, let us call this as C1 and this is C2, they are in between same two nodes. So this is a node A and this is node B. Okay, so this is the important part here. So C1 and C2 are between the same two nodes. Okay, and if they are in series, something like this, so from here we can clearly see they are at different nodes. Okay, so this is important part here. So this is our suppose C1, this is our suppose C2. Okay, if you want to redraw, because this circuit we can draw either like this or we can draw it like this. Okay, but if you draw it in the second part, when C1 and C2 are in series, we can clearly see that they are not between two nodes, same nodes. They are at a different nodes. Okay, so therefore, it cannot be drawn like this. So therefore, C1 and C2 are in parallel. Okay. So we can say they are in parallel. Okay. And so if they are parallel, therefore we can write that their equivalent capacitance, which because they are parallel, will be equal to C1 plus C2. So C1 is about twice C and C2 is also twice C. Therefore we get that C equivalent will be equal to 4 times C. This is our solution. Next question, same question, okay, but here it is now asked with respect to our charge density, and the distance between the plates is asymmetric. Okay, now they are not at the third plate is not at the center of it. So we are given that 3 conducting plates are placed parallel to one another as in the figure. The outer plates are connected by the wire. The inner plate is isolated, has a net surface charge density of our rho, the combined value from the top and the bottom face of the plate. What is the surface densities ρ1 and ρ2 on the top and the bottom faces of our inner plate? Yes, we have to remember that this parallel plate capacitor is basically a individual conductors. They are parallel to each other, and these individual conductors are going to have 2 faces. Okay, we can say this as a internal face or top face, or external face or bottom face. Okay, based on this, they are going to have 2 charge densities, okay, ρ1 and ρ2, sigma 1 and sigma 2. And so we are going to solve it not terms of this 5 centimeter, 8 centimeter. We are going to solve it in general terms, like distance is our d1 and other distance we are going to call this as our d2. Okay, later on we can just substitute. So we can say the plate's distance is a d1 and this is our d2, and it is capacitance having C1 and its capacitance is our C2. Okay, area is both our same, of all the plates is same. And so here also the outer plates, okay, they are connected by a wire. So let us call this as plate number 1, 2 and 3. So 1 and 3 are connected in wire, so they will be at same potential, whereas 2 is independent, means this is not connected, so we can say it is having a different potential. Okay. Therefore let's start from the potential part only. So we can say 1 and 3, these are connected with the help of the wire, and therefore we can say they are going to have same potential. And let's call that same potential, that is our V, and let us take that value equal to over 0. Okay. And the plate number 2 is our isolated plate. So this plate number 2 is our isolated, and it is given that this plate number 2 is having a total surface charge density as our sigma. So we are given this as total surface charge density. It is given as sigma, and it is also mentioned that this is isolated plate number 2 has a surface charge top and bottom is given as sigma 1 and sigma 2. So it will be equal to sigma 1 plus sigma 2. Okay. And so one important thing is that the plate number 2 is isolated, so obviously its total charge will be fixed. Okay, therefore we can say for this plate number 2, its total charge is fixed. And our plate number 1 and 3, which are connected together, so they are going to behave like a single conductor. Okay, so we can, from here also we can say that these are going to behave like a single conductor. And so once again, we like in the previous case also, so these C1 and C2, they will be acting like a parallel plate capacitor. Okay, we have already proved or discussed this in our question number 1. So we can say that our C1 capacitance is between plate 1 and plate 2, and our C2 is between our 2 and 3, and this C1 is in parallel to our C2. Okay, that we have already proved, or rather we can say discussed. And once again, let us remove this A and let us call this as node A, and this is node B, and obviously this will be also node A. Okay. So the outer node, node A, is nothing but shorted outer plates whose potential we have assumed is equal to 0, and inner we are going to assume that it is having a certain potential, that is our B. Okay. So we can say that our node A, and this node A is at a potential which is equal to 0, and then we are having node B, and in that case we have to assume that it is at a certain potential, and that potential, let us suppose, is our V. Okay, and node B is nothing but our isolated inner plate, so we have to remember this. So this is our inner plate, which we have denoted as B, and node A is the short of our short circuited plate number, sorry, this is plate number 2, not B, and is short circuited between plate 1 and 3. Now we can use the parallel plate capacitor, you can say basic formula. Therefore we can say that our C1, which is our top capacitor, will be equal to epsilon naught A, and the distance we have assumed D1, and C2, that is the bottom capacitor, will be equal to epsilon naught A upon D2. And we can easily find out the charges. So we can say the Q1 will be equal to C1 times V, and which will be nothing but our charge density multiplied by this our area. And similarly we can write our Q2, and this will be our C2 times V, and that will be a charge density multiplied by our A. And we can simply take the ratio, and from here we can say that our rho 1 rho 2 is equal to C1 upon C2 is equal to D2 upon D1. So we can just drive this part. And in the question or in general, we also know that because of the conservation of charges, especially with respect to our plate 2, we can say conservation of charges, and which we have already written, that rho sigma is equal to sigma 1 plus sigma 2. And especially this equation is already indirectly mentioned in the question, that this row 1 and row 2 are the top and bottom faces of inner plate. Okay, so this is our inner plate. So it is given as row 1 and bottom is our row 2. And their combination is said to be given as surface charge density as our rho, sigma. And from here, this equation, we can write that our rho 1 d1, well, not rho 1, but sigma 1 d1 is equal to sigma 2 d2. And from here, we are going to substitute value of sigma 1. Okay, so let me rewrite it. So this will be sigma 1 and divided by our d1. So we are going to use the sigma 1 and substitute it in this equation. So we get this as our sigma 2 we can take as common. Okay, so we can just write it directly. This will be coming as 1 plus d2 upon d1 times sigma 1, or we can also write this as our d1 plus d2 divided by d1 times sigma 1. And similarly, we can write that our sigma 2, one second, okay, we need to find out sigma 1. We can just do the reverse of it. And from here, we can say that sigma 1 will be equal to our sigma multiplied by our d1 and d1 plus d2, which we are supposed to find out. And similarly, we can say that our sigma 2, one second, I have written it correctly. Let me, yeah, the difference will be of our sigma 1 d1 and sigma 1 is this d2 by d1. I think this looks d1, yeah, this looks good. So this we get this as sigma 1 d2 and this comes as d1 plus d2. So these are the respective charge densities. Same question like the first part, but in this case it is specifically asking about the charge densities. Same question. Okay. And only thing that here there is a asymmetric. Okay, it is given as 5 centimeter and 8 centimeter. We derived it for general part, that is our d1 and d2. So we can just substitute d1 as 5, d2 is 8. Okay, and we are going to solve it. But other values are not given to us, so we can just keep as it is. And if we want, we substitute it, and otherwise we can keep it as it is. So this was our second question. Now we come to our third question. Third question is also somewhat same, but a little bit different way it is being presented or asked. So we are given that 4 conducting plates lie parallel to each other as shown in the figure. The spacings between are arbitrarily but small compared to the lateral dimensions. The top 2 plates are connected by a wire, so they are at the same potential, and likewise for the bottom 2, a total charge Q1 resides on the top 2 plates and total charge Q2 on the bottom 2. What is the charge on each of the 4 plates? A basic figure we can easily draw. So we are given as a 4 plates. So these are the top 2 plates and these are our bottom 2 plates. Okay. And the separation is asymmetric. Okay, there is no relationship between the separation between the plates. And these plates are interconnected. So this is connected to the wire and these two are also connected to the wire. So let us call this a plate number 1, 2, 3 and 4. And we are given that this top plate is having a total charge of our Q1, okay, and the bottom one is having a total charge of our Q2. Okay, so this is the basic question, and we have to find out the charge on each of the 4 plates. Okay, so we have to find out, and obviously 1 and 2 are connected, so they will be at same potential. 3 and 4 are connected, so they will be also at the same potential. Therefore we can say 1 is connected with 2, so they will be at same potential, and the total charge on this is given as a Q1. And then we are having plate number 3 and 4, they are also connected, so they will be also at the same potential, and that will be our charge is given to us as Q2. And obviously we know that each plate is going to have two faces, top face as well as a bottom face. So we can accordingly denote their charge densities with respect to each face. Therefore we can say that each plate has two faces. Each plate is going to have two faces, and so let us, for plate 1 it is going to have two faces, so we are going to call it as a top face, is having a charge density of our sigma 1 top, and then it is going to have a bottom face, and bottom face we are going to call this sigma 1 bottom. And similarly there will be our second plate. The second plate we are going to call this as a top as sigma 1 2 and bottom as sigma 2b. Similarly our face number plate number 3 we are going to call this sigma 3 top and sigma 3 bottom. And then we have a plate number 4. Once again we call this as a 4 top and we call this as a 4 bottom. So we are having total 8, total you can say there are 4 faces, so there will be total 8 surface charge densities. And we assume that this distance is given as d1 and this distance plates is given as our d2. Okay, and this we call this as a d3 and this we call this as a d2, because this will be also the 2 and 3 will be also our parallel plate capacitors. And we know that in case of our this parallel plate conducting plate system, the outer surface charges are equal. That we already know. So we can say that outer surface charges are equal. Outer surface charges are equal. Or we can say, based on this, we can write that our sigma 1 top will be equal to sigma 4 bottom. Okay, and let us call this as our sigma out. Okay, and this outer basically means the outermost. Okay, so let me rephrase it. This is our outermost. And so this is also, we can say, if we use our Gauss law pillbox concept, we can also write that our same sigma 1 top will be equal to sigma 4 bottom. This is also true from our Gauss law with respect to our, because using the Gauss law to a pillbox concept. Okay. And we also know that the total charge will be always conserved. It means the sum of all charges will be also always equal to Q1 plus Q2. because the respective charges are given to us as a Q1 and Q2. So from here we can also write that total charge must be conserved. Total charge must be conserved. So from here we can write with respect, because we are dealing with surface charge density. Okay. So in terms of our charges, we can write this as our sum of all surface charges is equal to Q1 plus Q2. Okay. And like we said, that since we know that the outer charges are equal, so it means they all together with the inner charges should be equal to Q1 plus Q2. Therefore, in terms of statement or equation, we write that our twice charge density of our outer surface plus inner surface charges will be equal to Q1 plus Q2. And we also know that because inside each conducting plate, or we can say that electric field inside each conductor is equal to 0, because that is our standard notation or concept. And we can also, because we are here dealing with the charge densities, therefore we can say that the field inside a conductor due to all surface charges must vanish, or they should be equal to 0. Therefore, in terms of our parallel plate capacitor, this means that the facing surfaces which are facing with one another must be having equal and opposite charge densities. This looks a little bit complicated, but it is very easy to understand. So let me start with the electric field. We know that our field inside each conductor is 0, and therefore we can further write that our field inside a conductor due to all surface charges must vanish. Say field due to field inside a conductor due to all surface charges must vanish. And specifically in terms of a parallel plate capacitor, so we can say for parallel plate capacitor, we can write that the facing surfaces of any gap have equal and opposite charge densities. So specifically in terms of our parallel plate capacitor, we can write that the charge density of the first bottom should be equal to negative of charge densities of second top, because they are facing each other. Similarly, we can write surface charge density of our second bottom should be equal to negative of charge density of our third top, and charge density of our third bottom should be equal to negative of our charge density of our fourth top. So we can just say that suppose this is one of the capacitor and this is other one of the capacitor. So the facing will be this one. So these are the internal facing one. So one is having a bottom part and other one is having a top part. Okay. And their surface charge density will be our equal and opposite. But we also are given that the our top that plates 1 and 2 is having a net charge of Q1, and the plate 3 and 4 is having a net charge of our Q2, that is given to us. Okay. So we are going to use this charge constraint because the net charge is going to conserve. So the top 1 and 2 will be always having Q1, and the bottom 3 and 4 is going to have a total charge always, that will be Q2. So we are going to use our charge constraint and we start with our top pair. Top pair is nothing but our 1 and 2, and this 1 and 2 we know that total charge should be always equal to our Q1, and each plate is having a two surfaces, one is top, other one is our bottom. So we can say our Q1 will be equal to 1 top plus 1 bottom plus second top and our second bottom. But we already know that our 1 bottom is equal to negative of our second top, that is our given to us. Okay. And we also know that our this here is so Q1 top and the bottom is having a same surface charge density, which we have denoted as our out. Okay. So we simply substitute it. Therefore, we in terms of this our Q1 top, we can write this as our surface charge density of our outer plus this comes as a 1 bottom, and our 1 bottom is equal to our 2 negative of our 2 top, and what else, 1 second, 1 bottom, 2 top, and this comes as plus sigma 2 bottom, and this entire is equal to our Q1. Therefore, 1 second, I missed something. Sorry, I wrote same thing repeated. Okay. This will be equal to negative of 1 bottom. Yes. So these two terms are going to cancel out with each other. Therefore, we get that our charge density for the outer plus our for 2 bottom is equal to our Q1. So we got one of the equation. Let us call this equation number 1. Now we come to once again to same part, same calculation we are going to do for our bottom pair. Bottom pair means plates 3 and 4. So we are having our bottom pair, and bottom pair is our 3 and 4. And once again we are going to write it as our, because they are having this is 3 top plus 3 bottom plus 4 top plus 4 bottom, and charge is given to us our Q2. And once again we know that our this 4 bottom is equal to our sigma out. Okay, because they are, we know for our parallel plate the outer is going to have the same charge densities, and 3 bottom is equal to negative of our 4 top. So we simply replace it and we get this as our 3 top and minus 4 bottom, 4 top, sorry, and this will be our plus 4 top, and this comes sigma out is equal to our Q2, and here this 2 times cancels out, and this gives us that our 3 top out is equal to our Q2, and this is our equation number 2. Now we are going to use equipotential condition because plate number 1 and 2 are connected and plate number 3 and 4 are connected with each other. So they will be respectively at the same potential. So we have our equal potential condition, and so we are having plate 1 is connected to plate 2, okay, and they will be at the same potential, and we can also say that the voltage across the gap is equal to 0. So let us suppose this is our V1, and we can write this as our charge density with respect to our bottom divided by our epsilon naught and multiply our D1 is equal to 0. And therefore from here we can say that the charge density at the bottom is equal to 0, because this is plate number 1 and this is plate number 2, and they are connected with the help of a wire, but only the inner surface of plate 1 and plate 2 are connected. So it means they are respectively, we are going to get the charge density of one bottom is equal to 0. And we also know relationship between the bottom and the top. Therefore we can say the charge density of the second top, which is equal to a negative of our charge density of the bottom, so that will be also equal to 0. And then similarly we come to our plate number 3 and plate number 4, and let us suppose that potential is a V2, obviously, which will be equal to 0. There is no potential difference. And 1 second, I think I missed something. Okay, let me call this as V3, not V2, because the distance we have taken is our D3, much more easier. And this will be coming as our 3 bottom divided by epsilon naught and times our D3, which is equal to 0. So we get this as sigma 3 B3 is equal to 0. And we know that our 4 top is equal to negative of our 3 bottom. So this will be also equal to 0. And so now we are going to use equation number 1 as well as equation number 2 and get the final answer. Okay. So we can say that from equation 1, okay, we can write that our charge density for our bottom is equal to our Q1 minus charge density of our out. Okay. And from equation 2, we can write this as our 3 top will be equal to our Q2 minus our charge density for our outer. Okay. And we already know that our charge density with respect to our 2 bottom is equal to negative of charge density of our 3rd top. So it means these two are equal but with the negative sign. Therefore we can say that our with respect to negative sign we can just equate them. So we can say this is Q1 minus charge density for our outer surface is equal to negative of our Q2 minus charge density for our outer surface. And So from here we get that a Q1 plus Q2 is equal to 2 times the outer part, or from here we can say that the charge density for the outer is equal to Q1 plus Q2 divided by 2. So this is our one of the solution. We have to find out the many parts of it, and we can also write that the charge density for the second bottom, we substitute this back here. So we get this over Q1 minus of Q1 plus Q2 upon 2. And this gives us Q1 minus Q2 upon 2. So we got the charge density for our second bottom. Similarly, we can write the charge density of our 3 top, and now we are going to use in this equation, we get this over Q2 minus Q1 plus Q2 upon 2, which gives us our Q2 minus Q1 upon 2. So we also got our charge density of the third top. Okay. And rest of charge densities we have already calculated because they are equal to 0. Okay. So we just found out that this value is equal to 0. So we got the respective charge densities. Okay. And we have to remember, yeah, I think that completes the question. Okay. Because we were required to find out the respective charge densities. Yeah, I think this will work. Okay, and in this case, we have to remember that the total charge 1 plus 2 will be always equal to Q1, and 2 plus 3 charge will be always equal to Q2. That is bound to happen. We cannot, there is no, you can say, dispute about it. If you want, we can just add it and find the answer. Okay, so we got the respectively the charge densities of all the faces. Plate 1 is equal to,
I found
sorry,
this on the web for. What does the
sorry about that. Oh. Okay, so we come to next question then. And this is also with respect to our parallel plate capacitor, but it is now a, you can say, cylindrical capacitor, okay, or it is basically a disc. And in this case, we can just use it to, we are going to solve it in a little bit different way that is much more convenient, and we have done this, you must have done this multiple times. Okay. And we are given that we are having a 2 discs. Suppose this is the top one and this is the bottom one, and each is having a radius of r, and the distance of separation between the two is given to us over s. And the surface charge density of the top one is our plus of sigma, and bottom one is our minus of sigma. Okay. And we have to find out the electric field at the center, small distance of the positive disk. Okay, so we have to find out the electric field somewhere here, that is small distance from our center of our this top plate. And in this case, we are not going to take this as a parallel plate capacitor, but we are going to consider this as our you can say 2 discs. We are going to take disc 1 as independent, disc 2 as independent. So this is our disc 1 and this is disc 2. And respectively, independently, we are going to find out the electric field at this point. That is point P. Okay, because we know the standard formula for electric field at a point which lies on the axis of a you can say disk. Okay, so we are going to use that particular concept. Okay, there is, and the total electric field will be nothing but the superposition of disk 1, electric field due to disk 1 and electric field due to disk 2. Okay, so we are going to treat them as ever. These are having two separate charge disks. We are not going to treat as a parallel plate capacitor. Okay, we are not going to treat as a parallel plate capacitor. So we are going to treat the capacitor as two separate charged disk. So it means we are interested in the total electric field or net electric field will be the superposition of disk 1 as well as disk 2. Okay. So that will be nothing but superposition of disk 1 and disk 2. Okay. From the looks of it, it looks like we are having a parallel plate capacitor, but it is much more convenient that we take disk 1 D1 independently, disk 2 D2 independently, and then we use the principle of superposition to get the answer, net electric field at point P. So let's find out the field from a single charge disk. Field from a single charged disk. Okay. And suppose we take this as a z-axis. So this is our z-axis, and this point P, in general, for the start, let us assume that it is at a distance z from the origin. So we can just write the formula and then divide that formula according to our requirement. And therefore, we can say that for field from a single charge disk having charge density sigma at a distance z. Therefore, we can write that electric field due to a disk at a distance z will be equal to sigma upon 2 epsilon naught, and we 1 minus our distance z and z square plus r square and its square root. Okay, and we have taken z this as modulus because if z is greater than 0, so we are going to take it as positive, and otherwise it will be our negative. So we can say for z greater than 0, that is above the disk, we can write that our electric field due to our disk at point z will be equal to Same formula. Now we just remove the modulus part. Z square plus R square and its square root. And now we come to this particular question. So we place that our positive disk is at Z is equal to 0. So this positive plate is at Z is equal to 0. And obviously this negative plate, because the distance between the two is S, so this will be at S is equal to Z is equal to minus of S. So you can say that our positive disk, which we have considered disk 1, is at Z is equal to 0. Therefore, we can write that our negative disk, which is our D2, it will be at Z is equal to minus of S. And we want that point P is just above the positive disk. Okay. So field at point P, and this point P is said to be given just above our positive disk, which is nothing but our D1. Therefore, we can write that this point P is at Z is equal to a small distance, that is epsilon, which is approximately equal to 0 positive, because that distance is given to us a very small. And let us rewrite the electric formula with respect to the given condition. Therefore, we can say that for our positive disk, that is our D1, which is at Z is equal to 0, charge density is our plus sigma. And we are going to find it at Z is equal to epsilon, which is very close to 0 positive, just above. Okay. Therefore, we can say that electric field positive will be equal to sigma upon 2 epsilon naught 1 minus epsilon, and this comes as epsilon square plus R square and its square root. And now we can use the approximation. So this will be approximately equal to sigma upon 2 epsilon naught, and this comes as 1 minus 0. Therefore, electric field due to the positive disk just above is equal to upon 2 epsilon naught, and it will be upward direction. And now we come to our negative disk. So we are having our negative disk, which is our disk D2, and that negative disk is at S is equal to Z is equal to minus of S, and charge density is our minus negative. Okay. And we have to find out it at Z is equal to epsilon small. Okay. And therefore, because this distance is with respect to positive, but we are calculating it with respect to negative, therefore we can say from negative disk, the distance is supposed at D, then this D will be equal to epsilon minus of minus S, which comes as our epsilon plus S, and this is very small, so approximately this is equal to S. So this is our approximation part. Therefore, now we come to electric field due to negative is equal to minus upon 2 epsilon naught, and it comes as 1 minus of S, and is our S square plus R square and its square root. And its direction will be the downward direction, directed downward towards the negative disk, because And if we are only interested in the magnitude part, we can write upon 2 epsilon naught 1 minus s upon s square plus r square and its square root. Therefore, total field, if we take upward as positive, therefore we can write that our total field, suppose we have E, it will be equal to our the superposition modulus negative. Okay. So this gives us sigma upon 2 epsilon naught minus sigma upon 2 epsilon naught 1 minus s upon s square plus r square and its square root. And we can just rewrite it. So we get this as E, and if we open the bracket, these two terms are going to cancel out, and this will be coming as sigma upon 2 epsilon naught s upon s square plus r square and square root. And if we are already given that value of s, separation between the plates is very much smaller than the radius. Therefore, we can use the approximation that our net electric field will be equal to sigma times s divided by 2 epsilon naught times r. Okay. And it will be the upward direction. This is net electric field. So as per the question was supposed to be dealt as a parallel plate capacitor, which is in the form of the disk, but we dealt it as a two independent charge plates. Okay. And that is much more convenient to find out the value of electric field. Next question. So in this case, it is given, consider a setup with two n parallel plates. First, third, fifth, etc. plates are connected by wires. Likewise, second, fourth, sixth plates are also connected. What is the capacitance of this system? What does it equal when n tends to infinity limit? Okay. So we can just draw the basic figure. So we are given two n parallel plates. So this is 1, this is 2, 3, 4, and so on. This will be 2n minus 1, and this will be over 2n. So this is 1, 2, 3, 4. This is about 2n minus 1, and this will be about 2n. Okay. And so connection is already given to us, that is first and third are connected. So this first is connected with third, and our second is connected with fourth. Okay, so all the even ones are connected and all the odd ones are connected. Okay. So, and they are equally placed. Okay. So we can say that the distance spacing between them is given as s, and the area of the plates is given as our A. So we are mainly interested in how they are connected. So we can say that the plates 1, 3, 5 up till 2n minus 1, they are connected with each other. Okay. And obviously they will be at same potential. Therefore, we can say they will be at same potential. And let us suppose this same potential is given as our potential of our odd, because they are simply odd numbers. And similarly, we are having our plates. These are 2, 4, 6 up till 2n, and they will be connected with each other. And once again, they will be at same potential. And that same potential is, suppose, our potential E1. Therefore, we can say that this creates basically alternating parallel plate capacitors between two compounded electrodes. So in general, we can define this entire setup as alternating parallel capacitors between two compound electrodes. And we are mainly interested in the, you can say, how they are connected. There are two only options. Either they will be series or they will be in parallel. Okay, so let us understand the pattern. Okay. So we are having a gap 1, and this gap 1 is between plates 1 and 2. Okay. So basically it is between odd and even. Then we are having gap 2, and gap 2 is between our plates 2 and 3, and this is between even and odd. Even and odd. And similarly, let's write for one more, that is our gap 3, and this is between our plates 3 and 4. Once again, it is between odd and even, and this process will be continuous. And so it means each gap is going to generate a individual capacitance of our parallel plate capacitor whose formula is known to us. Okay. Therefore, we can say each gap forms a capacitor, and which is suppose of C naught, it will be equal to epsilon naught A divided by S, and between two compounded conductors, between two compound conductors. And let's count. Now we are interested in that we are going to basically count the capacitors, and we know that all these capacitors are in parallel because they are connected between the same two nodes, okay, odd plate node and even plate node. We can clearly see that it is always combination of our odd plate node and even plate, okay, because if you look closely, this question is nothing but the extension of question number 1 as well as question number 2, which we did right now. Okay. So we can say that the capacitors, they all in parallel, because they connect same two nodes, and the same two nodes are our odd plate node and even plate node. Odd plate node and even plate node. Therefore, these all are in parallel. And obviously the total number of plates are 2n, therefore the gap will be equal to 2n minus 1. We can say number of gaps will be equal to 2n minus 1, and we know that our each gap is going to give a capacitance of a C naught, whose value is our epsilon naught A upon S. So it means total capacitance will be equal to, because all of them are in parallel, so total capacitance, that is C, will be equal to our 2n minus 1 times our C naught, that is our epsilon naught A upon S. And this A upon S is nothing but our C naught. Therefore, we can write this as our 2n minus 1 times C naught. Okay, so this is our total capacitance of our the parallel plates, which number is given as 2n. And finally, we are interested in that our limit n tends to infinity. Okay. So which also tells us that the value of C will also going to infinity. Okay. Because from the equation we can clearly see that C is proportional to our n, direct. So if n goes to infinity, the value of capacitance will be also going to infinity. So these were the 5 questions for today, and in these 5 questions we dealt with our, you can say, parallel plate capacitors, and who are connected, which are connected rather, in different combinations. Mostly they are connected, different plates are connected, okay, and each question is presented by a different type of challenge. And in some of the question they are asking about the charge densities. No doubt the plates are still connected with each other, but they are discussing about the charge densities. Then they are discussing about our, like in this case, our what is going to happen when their number of plates are very high. Okay, so these were basically how the capacitors are going to behave when their different plates are connected with each other. Okay, and these were all with respect to our parallel plate capacitor, except one question which was given for our parallel plate capacitor, but we solved it as taking as individual discs. Okay, we are supposed to find out in that case the value of our electric field. So what we did, we solved it by taking the individual plates. So we are given 2 discs, here disc number 1 and disc number 2. We are supposed to find out electric field somewhere here. So we treated this as independent disk as well as this as also independent disk. We didn't consider them as a parallel plate capacitor. Okay, and we solved it independently for this one and this one to find out electric field at this point. Okay, suppose this was point we taken as P, and then we use the superposition to find out the net field at point P. Okay, that is much more convenient with respect to taking this as a parallel plate capacitor and try to mug it up how to solve it. So much better approach, take this disk as independent, this disk as independent, and then use the superposition, try to find out the net electric field at point P, because point P is lying on the axis of the disk, and we already know the standard formula. And in this case charge was not given, the charge density was given, and they were opposite with each other. So positive is going to upward, negative is going to downward, and it is going to solve easily. So this was the only minor aberration here. We reformulated the solution as per our requirement, or we can say the easy part. Okay, so this completes all the 5 questions for today. Thank you.